What's up, everybody? We're going to now we are going to look at this backstepping control problem. Okay, and I rename this as problem 4. And in the previous video, we have talked about the general idea of backstepping controller, and now we are going to focus on this a little bit more complicated example. And in that example, we are going to focus on the robustness issue. Okay, and in additional additionally, we are going to focus on the parameter uncertainty. All right, so let's start here. This is our problem. Right, the problem statement is this. This is the dynamical system, right? And theta 1 and theta 2 are the parameters, right? And they are bounded by a and b, and these are a and b are the numerical values that we know, right? Okay, this assumption, right? And this is an assumption, and the problem is that find u as a function of x1 and x2, meaning the control law, right? And such that the CL stands for closed loop, such that when we substitute the explicit expression of u, right, in this dynamical equation, right, and x, right, goes to 0, s t goes to infinity. Okay, asymptotic stability. Okay, what we are trying to achieve. And okay, so first of all, this is an annoying term, right? Sine of x1, and it would be better for us to get rid of that, right? Change it with something that is more that is something that we are used to, right? Okay, and since we know something about sine of x1, what is that? Any sine function absolute value is bounded by 1. This is something we know, right? Because 1 and minus 1, right? Okay, so and since this term is also bounded by a, okay, we can in a general way change this theta 1 and sine of x1, we can change this by a times delta 1. And delta is the kind of term that you get used to, and it indicates uncertainty. Let me just type it. Whenever you see delta, right, and maybe delta I, because there will be delta 1, delta 2, right, etc. And okay, it will mean uncertainty. Okay, so all right, the problem now is this. And did I write this? Wait a sec. Yeah, let me type that as well. Okay, so this is assumption on delta I, right? And the problem that we are interested in is this. Okay, and now we are going to look at how we would use backstepping control algorithm to find a control law such that it will stabilize the system, you know, when these uncertainties present in the system. Okay, in the environment rather. Okay, and yeah, this is basically like sine of x1 being bounded by 1, right? Okay, and this value, again, this like the triangle of inequality, right? This term expression rather is an upper bound of this expression, right? And also since a is an upper bound of theta 1, right, theta 1, and we can change that by this, right? Okay, this is our new problem now. Okay, just right. Just consider that we are starting from this location. Okay, in the previous operations, kinda they were done to indicate there will be some pre-processing procedure, right? Okay, that was to indicate that. Okay, and again, like in the previous video, we are going to, and maybe it would be better for me to show, yeah, okay, just look at the structure of this dynamics. This is u, right? And this is, I'm going to indicate x up to, right? And in fact, because I don't want to write x1 x2 dot equals this whole expression, this expression, right? Okay, so I'm going to write x2 dot, and here you can see x1 and u are the terms that affect the x2 dynamics, right? And the output of that will be x2, and x2 is the only external term that affect x1 dot dynamics. Okay, of course this is not an official, you know, block diagram representation. This is like to indicate the idea. Okay, all right, so here, okay, so whenever you have, by the way, this has some structure, right? So it is not like we have u, right? And maybe I should show that something like this. Okay, and the output of that, let's say x, and this type of problem, and x can be like, when I say x, I mean x, like the column vector of, you know, whose entries are x1 and x2, right? And again, like when I say x dots, you get the idea. Okay, so this problem is more general, right? Harder. And let me get another color. Okay, so this problem, right, has some special structure that is useful to us, and we will use backstepping control, right? And because backstepping control is a type of control algorithm that can be used when we have this type of special structure. Okay, okay, it is, for example, this is a general structure. This problem is harder, but this problem is easier. Okay, all right, so maybe I can make things, I guess it can, all right, okay, I can left it there. All right, where we are here in this location. Okay, so like in the previous video, right, this is the typical parameter change, and as a result of that, because here we are looking at, and first we are looking at this part, and we are saying, hey, what, and let's say x2 is my input. Okay, x2 is my input. Let's focus on this problem. What would we do? We would probably use some function of x1, right, state feedback type of idea, and to stabilize x1. Okay, and in the previous video we talk about this extensively. Okay, and that's why I'm not going to, you know, go over that again. So the basic idea that we are going to swap this term with this term. Okay, okay, and And as a result of that, just by taking the time derivative, we get this, right? And again, by expression in z dynamics to isolate z2 dot, and we know this, we can substitute the explicit form of it, okay? And now we have this x1 dot, right? And this term, and we are going to change this term with this term, right? Okay, so here this is the dynamics, and of course you can change that x2, right, by that. And now what we have achieved, we have this problem by doing some transformation. Now we have x1 and z2, right? We could use z1, but yeah, this is the general, after, I mean, at this point, I mean the convention, right? The convention. And of course I'm using the Hasan Halil's Nonlinear Systems 3rd edition, right, textbook, and this is the convention that he used, right? And furthermore, I will not use this because I'm going to use this term, well, because I mean it will be easier for me to stick to that term, right? By not changing that term, I will have some I mean it will make things easier, right? Okay, to make things easier, okay, like in the general idea, we want this term to be less than 0, okay, and let's write the explicit forms of it, okay. And if we have z2 term, let's carry that over to z2 parenthesis, right? And here this term, right? And here this is z2 parenthesis term, and we call it term 2. And here we have 2x1, and we can simplify that, all right? And okay, let's zoom out a little. And okay, so at this point the problem is this. What's the problem statement? Let's talk about that. Find phi1 of x1, and I am looking at this such that, and also, by the way, let me find this, and also this, okay, such that this equality holds, okay. This is our constraint. So the problem is a mathematical feasibility optimization problem at this point, okay. So here, this, we want it, we can use this inequality and also this inequality. Let me wait a sec. Okay, this is constraint 1 and this is constraint 2, okay, and we have a general constraint, let's say constraint 0, and we basically, instead of using this constraint, now we are going to use this constraint 1 and constraint 2, okay. So this is the original problem, and now the problem is find phi 1 and u, okay, such that constraint 1 and constraint 2, right, are satisfied, okay. And okay, so let's explicitly analyze these equalities. For example, this is first inequality, okay, where w1 is a positive definite function, and also the same goes for the w2. W2 is also a positive definite function, okay, and the easiest, I think, positive definite function is this, right? So without loss of generality, we can just use this positive definite function, typical quadratic, okay, and here, and what we can do, we can isolate the term. This is the term that we like to find, right? And we can isolate it here, and then just doing some simplifications, okay, and we can reverse the order of the inequality, okay, and here, but usually we would just solve that. However, we have, let me express that idea here. We have uncertainty term here, and this term makes this problem compared to the previous problem, right, harder. So, but in general, we want this term to be greater than this term. So, and this is bounded, so we can just maximize this term, the right hand side, right, and using our uncertain term. Okay, so let's, I'm really slow today, right? Okay, this is our left hand side term, and we are going to maximize that, okay, and this is a general inequality, right? This is a function, and this is the maximum of that function, so of course it will be greater than this value, right? Okay, and let's just focus on this part. Here we can see that here, and this is an optimization problem, right? And we can just carry that max into that location here, right? Okay, and since this is a positive number, and this is the, I guess, important part of that operation, since a is a positive number, we can just carry that to that location, right? And then now, what is the value, right? What is the value of that expression? Explicitly, the numerical value is that this is 1, right? It's the easiest maximization problem ever. So, and by expressing the idea, right, this term is greater than this term, right? Okay, just a change of variables, and whenever you do that, I would recommend you to just have a table, construct a table, and just put that new expression that you introduce, right, so as not to get yourself confused, right? And okay, this will be called k here, and since we want to find phi 1, we can just use find phi 1 such that this expression is equal to that expression, right? Okay, so because it would satisfy the, right, this satisfies this, right, in a way sufficient condition. So we are just, every time we are changing our condition by a sufficient condition so as to make the general operations easier, okay, and by solving phi 1 we have this now. Okay, right. And whenever you solve phi 1, I would recommend you to have also phi 1 dot, because it's likely that you are going to use that in the next, I guess, function computation stage when you are dealing with backstepping control. Okay, all right. So here now, this was the first stage, and this is the second stage. In the first stage, we have computed phi 1, right? Now we are going to compute u, right? Okay, and this is our inequality. Again, we can swap this term with this term. Okay, and here, since we have phi 1 dot, we can explicitly write by using the dynamics. Here, this is x1 dot, right? X1 dot is this here. I am glossing over that. It may look like I'm glossing over some stuff, but you can download this docx file from the GitHub link down in the description below. Okay, and since we have talked about the general idea of backstepping control, right? The kind of operations that we do here are similar, right? Nothing has changed. And so this is the explicit form of this term, right? Okay, and now this can, okay, minus k, this is minus k, right? And here, and just distribute that term, we get this, and just distribute k, right? Okay, we now have this term. And what can we have as well? Yeah, so here, these three terms are the terms that you know in a way. I mean, you want to know u, but these two terms, right, they are not uncertain. However, here the other two terms are the terms that have uncertainty in them, right? So to make things easier, just use this change of variables. Again, a new variable we have defined, right? So in the previous stage we defined what k, right? And now I don't remember what k was, but now we defined v, right? So let's enter that to our table. Okay, so the problem is find v, right? Well, let's distribute this z2 term. Okay, explicitly we have this, and let's isolate v term. This is v term, right? Okay, and let me find, yeah, and then let's reverse to inequality. Okay, right? So this term here and this term, these are inequalities, right? So again, in the previous idea, we are going to find an upper bound of that function, right? And these are our tuning parameters in a way, right? And this is the function, and this is the upper bound of that function. And of course, since these three terms are linear, right? And when I say linear, I mean we can just decompose that in that fashion. And since this term doesn't depend on delta I, the uncertainty, we can just write it in that way. And I am looking at this, b is positive here, b is positive, and also this square term is positive, right? So we can carry them over here. And also we have a and k terms are positive. Okay, so again we can carry them over to that location. All right, and now this term can be also upper bounded by this term, right? It will make sense if you just try to understand. Okay, and here again one other term, it can be upper bounded by this expression, right? Okay, and now we can change that, and so this is this term. Okay, and by using these two upper bounds we can find another upper bound to that function, right? And just we can focus on that upper bound. Now the problem here, the problem that we are looking at is this, and we can here, this is again the easiest maximization problem, and this is the delta 1 version of it, right? And just we can type 1, right? And this absolute value of z2, right? And then here we are looking at this, and there is no operation here from what I can see. Yeah, and we will use that, and you remember that from sliding contour, and we can just, because we are trying to isolate v, right? And so we don't want any z term here, but we cannot just get rid of the z terms like that, right? Because we don't know the sign of z, and we only can cancel the positive terms if we are dealing with inequality, right? And that's why we can write this, and here we can factorize that, and here we can get rid of the z2 magnitude term now, and this is the inequality we are looking at now, and again we can reverse the inequality. All right, and we can swap the inequality with the equal sign because we want to find v, and here this manipulation is kind of, that looks tricky. We are going to get that to left hand side, and let's say you do that, okay? But here's the thing with the sine function, and I think it's interesting as well. And sine function, the reciprocal of it is equal to itself, right? So you can just see that by checking these two tables, and let's say sine of z1 is positive, or let's say z2 is positive, and sine of z2 is 1 as a result of that, and this is also 1, right, here. And since sine of z only can take two values, right, and 1 and minus 1, again these are the two conditions or two scenarios, right? Okay, and so this is the term, now if we can look at this here, The only term maybe you don't know is z2, but z2 is the term that we define in our table, right? This is the first variable actually, right? Okay, so what I'm trying to say is that z2 can be expressed as a function of x1 and x2. Okay, so all of the terms, another way of saying that, we have defined v, the virtual input, as a function of x1 and x2. Okay, all right, that looks quite messy. Okay, and yeah, as a result of those operations, the control law is computed to be, right, here, this is our uv definition, and first we define v, right, and here the k value, a is the term that we know, and this is v, final term that we have determined, right, and this is z2, and this is phi1. Okay, so okay, here this is our control signal, and v, what is v? V is this. Okay, is there something that we don't know, where there is k and z2? Okay, the k is defined here, right? Let's look at the left hand side. Do we know all the terms? Yes, we know all the terms here. Okay, so what is z2? Let's look at the left hand side. Do we know all the terms? Well, we don't know what phi1, right? Here phi1 is this. Okay, let's look at the again left hand side. It's like a tree structure in a way. Yeah, we know everything here, we know everything here, and okay, so we have this control law. All right, now let's look at the sliding mode control problem, and we will solve the same problem but using the sliding mode control framework. Okay, again the exact same problem, right, and it will be, the answer, right, will be quite similar to that, to what we have found by using backstepping control, right? And again, this is our problem, and in the first stage we are going to use this change of variables, and so this 1 2 3 4 5 6, these 6 sub blocks, they are same, right? And okay, so this is our starting point. Okay, and again this is v dot being negative inequality, and by substituting the x1 dynamics here, right, and z2 dynamics here, we have this, and we can put this z2 term into the term 2, right, and or into that z2 parenthesis to have term 2. Okay, and this is the final inequality that we need to solve for, and I am looking at this again here. This is part 1 and this is part 2. Okay, here this is part 1 and this must be less than or equal to minus times a positive definite function, and again the same goes for that part 2, right, here. Okay, we can see that this must be less than or equal to and a positive minus w2, where w2 is a positive definite function. Okay, let's start from this inequality. Okay, without loss of generality, let's swap that with this quadratic term, and let's isolate phi 1. Okay, and let's arrange that, factor that, group the terms, and let's reverse to inequality. Okay, and this term has uncertainty in it, so we want to find a bound, an upper bound in this case, and since x1 square is a positive term, that we know it is positive because square, right? And we can just carry that over, and here this is the term that we are looking at, and basically we can just swap that term with that term, and this is, again, a is a positive number, so we can put this here, and here again the same thing that we've been using, right? And we have this term as 1, and again this is the inequality, right? So again the same type of variable change, right? Here, okay, by putting k, we have this, right? Okay, and since we want to find phi 1, let's swap that inequality with equal sign and solve for phi 1. Here we have this, and this is linear, by the way. It's like interesting, right? Okay, and by using this, the sliding manifold is computed as, yeah, you remember we have this type of variable change in the first step in backstepping control, right? Okay, and actually this is, or what we call we've been calling z2 is s in sliding mode control. Okay, so another way of saying that s equals this term, and is our sliding manifold, right? Okay, you remember what was the general idea of sliding control is, right? We just define a manifold, right? And wherever we start, we just like go to that manifold in finite time, right? Finite time, and then we will asymptotically go to that state, the equilibrium point that we constructed, all right, or the desired point, I guess, in this case. Okay, and here this is s, right, equals 0. This is our sliding manifold because we slide on it, right? Wherever we start in state space, we just like in a finite time, not asymptotically, by the way, finite time, we latch onto that sliding manifold, and then asymptotically we converge into the desired point. Okay, this is the general idea, right? Okay, let me get rid of those. Okay, and explicitly it can be expressed as, all right, this is, so in a way this is our z2, right? Okay, and we can use the explicit form of phi 1, all right, and I also said, recall s dot equals minus k sine s, because this is the general term that we are trying to, this is the general term that we use, right? If you recall sliding mode control algorithm, right? We just construct our manifold, and then we express our S dynamics, and then by using some control algorithm, we make this is the left hand side. The left hand side look like this. Okay, we construct our U such that S dot equals this term, right? By canceling the other terms. Okay, and okay, this is positive, of course, is the general S dynamics that is used to obtain the control law. Let us look at the S dynamics. Okay, these are S, these are here, these are S, and let's find S dot. Okay, just take the time derivative, and this is our original problem, right? So we are going to substitute to the x1 and x2 dot terms. This is the term that we are looking at, and s dot equals this, right? So let us gather the known terms together and rename them, right? Okay, and these are the terms that we quote unquote know, right? And this is uncertainty including terms, okay, and containing terms. So let's swap the terms that we know, right, with this v, and we have this now. So find v instead of finding u, find v. Why? Because the reason is explained here. Now we have s dot equals uncertainty containing terms and plus the term that we want to use, we want to find, right? Okay, because x1 and kx2 is these terms we can just measure them because it's a safe feedback control, right? We can just measure them, right? From that is easy to manipulate. Okay, form that is easy to manipulate. Okay, let us gather the unknown terms together and rename them, right? Here, right? So let's gather the uncertainty containing terms, right? Okay, this is delta and this is delta, right? Okay, again let's rename them, right? And x1 and x2 here, x1 and x2. Okay, again the delta is the term containing uncertainties. Okay, right? And now that expression looks quite similar to what we have, I guess, analyzed, right, in the sliding mode control lesson previously, right? And this term, the problem is this: find v such that S dynamics are stable. Okay, and recall the objective is to have a resulting S dynamics of this. All right, the uncertain term delta is also known to be bounded, since this is the key point. This is uncertainty, however, that is bounded. Why? Because let's look deeper. We have delta 1 and delta 2, and they are bounded. Okay, and so this term can be written as this, right? Okay, since this condition, this information can be used to determine the upper bound for our uncertainty function, and this can be represented as this. Okay, so this is like this. Okay, And as a result of this, the S dynamics can be represented as, here this is original S dynamics, and this is the condition on the uncertainty or the constraint. To stabilize this dynamics, the proposed control law is this. Okay, so this is the kind of expression that we are familiar in sliding mode controller, right? Okay, and now another kind of, I guess you can say maybe generic control law that you can use, and it can be expressed as this. Okay, if you have this problem, you can just use this control law, right? This is the, I guess, proposition. Let's analyze that, right? Here, question. Let's look at this question where we have this as our S dynamics, okay? And this is our uncertainty. And this is the bound on our uncertainty, okay? Or uncertain here term. And find V such that S dynamics are stable and finite time stability, by the way. It's important, finite time stability. Okay, and the answer is this. If we use this control law, we can achieve finite time stability for S. Okay, and all right, let's kind of prove that idea here. All right, this is our starting point, right? Because this is the control law, we just swap that with V term here. Okay, and let us define that. Let us define this term. Okay, and let us also define that here. Okay, okay, this can be the case, right? Nothing wrong with that. And from here we have this, and the uncertainty term can be expressed as this, by the way, right? Well, let me explain that a little. And this is 1 and this is -1, so this is delta, right? Okay, and delta can take any values in that. Okay, so right, if we can, what about delta 2 times sine of S, or sine, any sine, right? Sine of any term, right? And because since we know sine of sine only takes -1 and +1, right? And if it takes +1, it will still be in that interval, right? And if it takes -1, it will still be in that interval. So we can just change that with, we can change this term with this term. Okay, I don't know how to prove that other than appealing to intuition. Yeah, but there must be uncertain term algebra. Yeah, this is correct type of course to make these operations more systematic. Maybe there is, and I don't know, but if there is no such a course, there should be. Yeah, this is my statement about what I fear about this. Okay, and that. Okay, so here this is S dynamics, right? And we made the change, we use this change of variables, and now let's gather the terms, and S dot equals term times sine of S. Okay, the term should be negative, therefore this is the inequality, and we can isolate delta 2 here, and we can find the upper bound again for delta 2 or the right hand side. Okay, and again this is 1, right? And finally this is the final inequality that we can use. Therefore, the suggested control law has the ability to drive the states onto the sliding manifold in finite time. Okay. And if we use that beta, and this is our origin of constraint on beta, right? And that would allow us to construct this V input control law, right? And that control law have the ability to stabilize S. Okay, so in a way it's proved, right? Okay, so let's remember where we were. Let us determine the bound on our uncertainty. Okay, this is our uncertainty and this is our bound, right? Okay, here let's explicitly write that, and let us try to find an upper bound for that uncertain term. I mean, let's try to find that, right? Okay, in a way. And again, we do the same type of manipulations, right? And since b is positive and since x2 square is like positive, we can carry them over. And again, a times k, okay? And whenever we have that type of term where our uncertainty times something that we know the sign of, right? We can carry that over by using this type of inequality, right? And we don't have any problem with that term, but we can change that with this. Okay, so this is where we are now, and this term and this term, I mean, it's like the terms that we know, and now explicitly we can write that. So, and this is our beta constraint, right? And this is our delta max. So we can just use that, right? Because beta of x must be this plus some positive term. Okay, but it must be greater than this term. Okay. Finally, the control law is written as, okay, this is our origin of, like, we first define v, right? And then we define beta and k, and then finally we solve for beta and s, and this is our uncertainty bound, and this is our some number, right, to add on to delta max to determine a beta of x function. Okay, so as a result of that, the control law is given by this. Okay, all right, if you can follow that problem, I will suggest you to download that docx, right, from the GitHub. Okay, so let us continue. And here, yeah, this is systematizing the problem. Let me say it again, systematizing the problem. All right, and this is the original problem. And first we look at the backstepping, and then we look at SMC, and now we are going to look at some, I guess, Lyapunov base method, right? Okay, Lyapunov plus backstepping plus SMC, I guess. Okay, because it has to, the problem we solve has to have some SMC type of arguments in it, because we are dealing with here nonlinear but uncertainty, right? Some type of robustness issues that we are dealing with here. Okay, so this is the original problem here. This is the typical inequality. This is the typical inequality. By arranging, we get this, right? Okay, and these are the constraints that we put on our original terms. Okay, this is like part 1, this is part 2. Okay, and this is the first stage. So from here to here it is quite standard, right? Okay, so let's look at the stage 1. Okay, so let me, okay, so this is what we have here. Choose w1, right, equal to that minus quadratic. Okay, I guess I should make that, yeah, okay, because w is positive. Okay, there's some error there, typo there. Okay, and now we have this. Okay, so distribute x1 over the parentheses. Okay, here now we have this. So arrange the terms such that phi1 is isolated. This kind of indicates that idea. Okay, so we have that. Okay, and find an upper bound for LHS, right, left hand side, and I am looking at this. So yeah, arrange the terms such that phi1 is isolated and phi1 term greater than other terms. Okay, yeah, express in that way. So we just put that in that form. Okay, so now we have this, and now find an upper bound. This is LHS, and we need to find an upper bound for that function. Okay, and here I use upper operation, right, and upper operation, yeah, upper is a made up operator, right, here k of x, right, k function k of x times f of uncertainty. Okay, and only operation that we, only function of that operation is this. Whenever you have that, just put that expression instead of that, right, and substitute that to make your problem, I guess, easier, right, because we are going to systematically solve that problem now, right? Okay, so let's only focus on this part. Okay, and since that operator is linear, we can write in that form, and here this is just positive number, right? We can put x1 square here, and a and x1 square, they're positive, we can get them here, right? And the only term that we need to look at is this, and we know that this is 1, right? Okay, so resulting term inequality is this. Okay, so solve for phi1, phi of x1, right, and first change that inequality to equality sign, and then solve for phi of 1. Okay, phi1 of x1. Okay, and again the same steps, right? We define that, we computed that, and focus on time derivative of phi1. Okay, because we are going to use, first we find phi1 and then we will find u, right? Okay, but whenever we find u, we will use phi1 dot expression. Okay, so this is it. By using this dynamics, right, by using this dynamics, substitute the x1 dynamics. Okay, and also explicitly write phi of 1. Okay, this is phi1 dot now, and by arranging the terms we get the phi1 dot expression. Okay, all right, now we will focus on u term, and this is the stage 2 inequality. Okay, and just choose this quadratic term, right, for w2. Okay, so we are here, substitute explicit form of phi 1 dots. Okay, this is phi 1 dots, and we know that now this is explicit form of phi 1 dots. Okay, gather the known terms in parentheses and rename them. Okay, and known terms, but let's note that. Okay, this is known, right, and also this is known, right? So here all the known terms together, and also delta containing terms. Okay, so let me zoom a little, and it says rename them, so let's use that. Let's define that variable, right? 2x1 plus kx2 plus u. Okay, all right, isolate v term. Okay, this is the term we can carry over, and I am looking at this now. We have this now. Okay, put it in the v term greater than or equal to other term. So swap the inequality. Okay, here gather the uncertain terms such that we have this form. Okay, this is uncertainty and this is uncertainty. Okay, use upper operator for left hand side. Okay, so let me really zoom, and this is where we are using upper, right, operator. This is a made up operator, so let's decompose that, right? Let's decompose further. Okay, so come on. Okay, all right, and if we record the function of upper operator, okay, this is the term for this term, right? And this is what we get by using the functionality of the upper operator with that term. Okay, all right, I'm again glossing over that, all right, because this is summary. Function of upper operator is defined here, right? Okay, and now we are here. Use this z equals absolute value of z times sine of z to isolate v. Yeah, this is what we strive for, right? Okay, and we are trying to isolate v, so from here again by using this equality here. Okay, and turn the inequality to equality to find v, and this is what we have. Finally, this is the definition of v, and if we isolate u, okay, and also v is this expression. Okay, so we can explicitly define u, and again by using z, the new variable, right? Again x1 x2, some transformation x1 and z2. Okay, and these are explicit form of u by using the explicit form of phi 1, right? Here this is our phi 1 of x1. This is it. So this is the control law that we need to use, and the problem is that if you look at that, I mean, it looks really complicated, right? For example, this is linear part of it, right? And by the way, this is absolute value, right? And this is also absolute value. Okay, and there's a sign factor here, So I don't know if you, how would you get that, how would you obtain that control law? By using some, I guess, optimization, numerical optimization, straightforward optimization scheme, right? It's not straightforward, in my opinion. Okay, this control law can be checked by simulating the following dynamical system. Okay, this is our dynamics, right? And this is our uncertainty, and this is our control law, right? And here, this is our dynamics, so we can just substitute the explicit form of u, right? So, okay, and should I explain that? Yeah, I guess explain that. It will be better for me to explain that. This is MATLAB code to simulate the closed loop system, and since our deltas are like uncertainty containing terms, right? And they have the uncertainty information. And okay, let's try to check the code. First of all, this is A and B parameters. Okay, so this commented out section is only to simulate it for a specific delta and delta 1 and delta 2. Okay, and here for ODE 45 you need t-span and initial point. Okay, and I also use that because I want to have that. Okay, I use that type of scheme to generate here in figure 1 and figure 2. Okay, and for that figure 1 I use axis 1, and for that figure 2 I use axis 2. Okay, and this is face portrait, and this is the state functions, right? State signals, and this is the origin, right? Okay, and I just check that type of logic by using the MATLAB's website, right? And so just use that if you want to have that type of scheme, right? Where you generate, okay, I will explain that more. This is figure 1 and this is figure 2, right? First of all, for x1 and for x2, okay. This is t and this is x, again x1 and x2, okay. And here, this is the face portrait, okay. This is only for one simulation, right? However, if we want to, run the same simulation, but with, random assigned stochastic parameters, right? We would use hold on type of command to just 1, 2, 3, right? And at the end, we will have a really messy, but indicating the general idea or the general idea of behavior of the system, we would have this type of figures, right? Okay, and first construct figure 1 and figure 2, okay, and then simulate and plot, okay, and then change the variables, and once again simulate and print or plot them, okay. Again, to change the variables, simulate and then plot them here, and this is the basic idea, okay. So let's look at here now. This is sigma and mu because two random variables, right? Okay, we have delta 1 and delta 2, so we will use normal distribution, okay. This command constructs or gives us some random generated number, okay, and 1 here, just one number, okay, and we multiply that with sigma, okay. This is the STD, like standard deviation, and this is the mu, this is the mean value, but mean value is 0, okay, because our this is delta terms have that type of constraint, okay. And in case we have this logic generates some number magnitude greater than 1, right? In case that happens, just equate it at some 0.9 or something, and do the same for delta 2 again, okay. And I guess the meat of the code is here, okay, this place, and this is only for plotting purposes, right? Okay, so this is OD45, okay, and this is our OD function, and we will now look at the function, and this is tx, okay, and the other terms are the parameters, all right, but we are saying that just focus on that t and x, focus on the two arguments, right? The other terms, they are just parameters that we assign, okay. And this is t span, and this is initial point, okay. And if you have x1, right, get x1 vector and x2 vector, right, okay. And I guess these two functions and these two functions are, I just googled them, right, and I found them to create this type of scheme, okay. And other than that, this is color, run style, line width, and parent. Yeah, this is kind of significant part. Just plot that to that axis, okay, and then again plot that to that axis, okay, here, okay. Again we have figure 1, and in figure 1 we have x1 here, this is figure 2, and in figure 2 we have x2, okay. All right, so this is plotting related issues, right? And when we are done with, let me look at the, yeah, we simulated 10 times, right, for 10 different delta values, okay. And this is for, I guess, aesthetical reasons, okay. All right, the final one, the function, right, OD function. This is t and x, and these are the parameters, okay. All right, this is just memory allocation and recover x1 and x2, okay. This is k, and this is our control law here, this is our control law, okay. And this is x dot, and this is x dot, x1 dot, and this is x dot 2, okay. So this is dynamics, and this is the control law. So together we have FCL of x, meaning the closed-loop dynamics. Okay, this is the general idea. Let's look at the result of that simulation. Yeah, MATLAB code output, closed-loop system simulation. Here we start from same points, 1, 2, x1 of 0, x2 of 0, okay. Here 1, 2, okay. And just do a simulation and change the delta value, and do another simulation, and change the delta value and do another simulation. And this is the basic idea, okay. And so we can see for all the delta values, right, all the data values. This is the close-up behavior. All right, and the states go to 0. And here, this is the sliding manifold, right? And this was the phi 1 of. This is the manifold, right? This is the manifold. Okay, so from starting point converges and latches onto the sliding manifold in finite time. Okay, right. So we look at 1 back stepping, 2 SMC, 3 systematic, I guess, approach, and fourth part of the video we look at the matlab codes and simulation results. Okay, so that's it. Please check the GitHub link down in the description.